In this video, we will look at the third type of chemical reaction studied in the AP Chemistry course. We've already looked at precipitation reactions and acid-base reactions. Now we're going to discover how you classify something as an oxidation-reduction reaction. An oxidation-reduction reaction occurs when the oxidation number of atoms participating in the reaction change from the reactant to the products. The oxidation number is sort of, but not exactly, like a charge. It is the charge an atom would have if all electrons were completely transferred from one atom to another. So in an ionic compound where we consider electron transfer to be complete, the oxidation number is the same as the charge. However, the difference comes in that oxidation numbers can also be assigned for covalent compounds where true complete transfer of electrons does not actually happen. So there's a series of rules for assigning oxidation numbers. It can be found on page 177 of your textbook, or it is right here on my slide. And so I would recommend, rather than me sitting here and reading it to you, that you pause the video and write down these oxidation reduction rules so that you can have them to reference as we go through some examples. I'll be referring back to them throughout this video. Because you need to know oxidation numbers and how to assign oxidation numbers in order to decide if a reaction is a redox reaction or not, the first thing we need to do is practice applying these rules. So one of the rules is that if you have a pure element, the oxidation number is 0 because the charge of all elements is 0. All elements are neutral. So the oxidation number for chromium is 0. Another one of the rules states that if you have an ion in an ionic compound, the oxidation number is the charge of the ion. So for B, the oxidation number would be positive 3. Now we get to the next one, and when I assign oxidation numbers, I usually start with the most electronegative element first. In this problem, chlorine is going to be the most electronegative element, and it tends to, when it has a charge, form a charge of a -1. So if chlorine's oxidation number is -1, and there are 4 of them, then carbon must have an oxidation number of positive 4, because in this neutral molecule, the total oxidation numbers have to add up to 0, kind of like they do in charges have to do in an ionic compound. The next example, strontium bromide, it is actually an ionic compound. It's a metal plus a nonmetal, and so the charges are going to be the same as the charges of the ions. Bromine will be -1 because it's in the halogen, the 17th column. Strontium will be positive 2 because of where it's located in the periodic table. All right, now we get into some that are more interesting because they start involving oxygen, and oxygen is very interesting when it comes to assigning oxidation numbers. Most of the time, oxygen's oxidation number is going to be -2. And in this case, since oxygen is paired with sulfur, there are 3 oxygens for a total oxidation number of -6. So sulfur must have an oxidation number of positive 6. Move on to the next one. What makes the next one different is that we now have an ion. So instead of like SO3, which had no charge written and it was a neutral molecule, nitrate has a charge written. It is an ion, a polyatomic ion. So in this case, the sum of all the oxidation numbers has to add up to -1 instead of adding up to 0. So oxygen, again, I'm going to start by assuming that oxygen's -2. It is most of the time. Nitrogen, we have to have a total charge of -1, and if we've got -6 oxidation number contributed by the 3 oxygen atoms, then the nitrogen must be a positive 5. Last example, when we get to things that have more than 2 elements, I tend to work my way from inside out. I'll start with the element farthest to the right because that that's the most electronegative, it tends to be the one that gets its most common charge. So oxygen is typically going to be -2. And I go from the inside out. So I'm going to do oxygen, then I'll come over and do the other outside. So I'm going to work my way into the middle. Oxygen first, then sodium. Sodium, just based on what I know about sodium as an ion, it tends to be +1. So I'm going to assume that that's what it does here as well. Then I figure out sulfur based on the other two elements. Oxygen's -2, there are 3 of them, so that gives us a total of -6. I have 2 sodiums, each with an oxidation number of +1, so -6 plus 2 is -4. Since this is neutral, I need another +4 from my sulfur, but there are 2 sulfur atoms over which to spread out that +4 charge, so each sulfur is going to have an oxidation number of +2. And that should give me a total oxidation number sum of 0 for this molecule. I just wrote a couple more examples up here because in our guidelines for assigning oxidation numbers, one of the guidelines says oxygen is -2 oxidation number except in peroxide. And so I want to give you a couple of examples of what I mean by a peroxide. These 3 compounds are all peroxides. This is called hydrogen peroxide. This is lithium peroxide. This is sodium peroxide. Very specific type of compound, but it does come up very, very often in redox reactions. And so you see them, although they're not common if we just look at all chemicals in the world, you do happen to see these chemicals a lot in redox reactions. All 3 of these have in common an element from column 1 in the periodic table. And column 1 tends to have a +1 charge. And you'll notice in all 3 examples, we have 2 sodium, 2 hydrogen, 2 lithium. If each of those atoms is +1, we have a total +2 oxidation number. The only way that that could possibly work out is if oxygen has a -1 oxidation number. So this is an example where this is called a peroxide. It is 2 oxygen atoms paired with 2 of a column 1 element. That's the most common way you see it. And in a peroxide, and only in a peroxide, oxygen will have an oxidation number of -1. I'm going to add one more example because I feel like when you start adding more than 2 elements, it can be more interesting. When I look at this is called potassium permanganate. Again, like I did on question G, I like to work from the outside towards the middle of the compound. So I'm going to start on the right with oxygen. If oxygen is not paired, just like those 3 examples before, this doesn't look like it's going to be a peroxide. I don't have O2. It's not paired with some atoms from column 1. So I'm going to assume that oxygen's oxidation number is -2. We've got 4 of them for a total of -8. Then I work on the outside. Potassium is most likely to be +1 because it's in column 1 on the periodic table. Then I use those 2 that I feel pretty confident, oxygen and potassium, to figure out what the manganese would be. So I have -8 for my oxygen and just a +1 for my potassium. So I need an additional 7 positive. And there's only 1 manganese atom, so that means manganese must have an oxidation number of +7. As with acids and bases, we will spend more time talking about oxidation reduction reactions later in the year. We're just kind of introing them now. But we need a couple of definitions before we look at these last few examples to decide if something's a redox reaction. It's called redox because it's a reaction that involves both a reduction process and an oxidation process. In a reduction, you have some atom that's going to gain electrons. And oxidation is an atom that's going to lose electrons. You have to have both processes because electrons cannot just be floating around homeless with nowhere to go. So you could also say that a redox reaction is about an exchange of electrons. One atom gains them, another gives them away. So that's hard to keep straight sometimes, so there's a couple of cute little mnemonics that you can use. The one that I learned in high school, which is my favorite, is Leo says GER. And that acronym stands for losing electrons is oxidation, gaining electrons is reduction. Another very common acronym to keep it straight is oil rig. And in that acronym it says oxidation is loss and reduction is gain. And you have to remember that it's electrons that we're talking about here. You can choose to use whichever acronym that you like. They're not really one better than the other. A very common question that you see on free response questions on the AP exam is a student claims that this is an oxidation reduction reaction. Do you agree with him or her? Why or why not? So this is practice in that type of problem. When you're given an equation and you're trying to decide if it is a redox reaction, you have to start by assigning oxidation numbers to all of the atoms in each compound. So we'll start here with mercury nitrate. In this one, oxygen is where I'm going to start. I'm going to assume it has a -2 charge. That gives us a total of -6 from these oxygen. And the nitrate polyatomic ion as a whole must have a -1 charge because NO3 has a -1 charge. So if this is -6, then the nitrogen has to be +5 because 5 minus 6 gives us -1. If I look at the mercury, nitrate, there's 2 of them, each one has a -1 charge. So the mercury must each have a +1 charge so that this is an overall compound with a 0-sum oxidation number. Potassium bromide, that's an ionic compound, so assigning oxidation numbers is basically the same as writing the charge for potassium and bromine. When I come over to the product, I look at bromine. Bromine has a -1 charge. So if there's 2 bromine, each -1, then the mercury has to stay +1. And the potassium nitrate, my other product, this nitrate polyatomic ion is in the same condition it was in the reactants. So that suggests that the oxidation numbers are going to remain -2 and +5 and +1 for the potassium. And that should work out. So if I look at this reaction from beginning to end, mercury stays +1, nitrogen +5, oxygen -2, potassium stays +1, bromine stays -1. Therefore, I would say no, this is not a redox reaction. All oxidation numbers are unchanged. All stay the same from reactants to products. All right, let's look at the next one. The next one, we start with 2 elements, aluminum and oxygen. Well, all elements have oxidation numbers of 0, so that's pretty easy to assign. When I come to the product, it's an ionic compound, so the oxidation numbers are going to match the charges of these elements, oxygen being -2, aluminum being +3. So it looks like this is an oxidation reaction. And it says that we have to identify what is oxidized and what is reduced. So the element that is oxidized is going to be the element that loses electrons. If something loses electrons, it's going to become more positive. So the aluminum, because its oxidation number changed from 0 to +3, it was oxidized. And oxygen was changed from 0 to -2. That means it gained electrons and it was reduced. Let's look at example number 3. Calcium oxide. It doesn't look like a peroxide because there's no O2 and not any elements from the first column on the periodic table. Oxygen is -2. Calcium tends to be +2, and that works out perfectly. For carbon dioxide, oxygen's -2, and if there's 2 oxygen, each with a -2 charge, or oxidation number, carbon's oxidation number would be +4. Now if we come over and look at the products, oxygen has a -2 oxidation number, calcium tends to be +2, so if I work my way towards the inside, I've got -6 and +2. That means that the carbon has to be +4. So in this case, it looks like all the oxidation numbers stay the same, so all oxidation numbers remain the same, so this is not a redox reaction. All right, we have one more example to look at today. Potassium permanganate, that was actually one of the examples I talked through on the last slide. Oxygen was -2, potassium's +1, leaving manganese to be +7. Here's an example, another example I gave on the last slide. Here's a classic, this is hydrogen peroxide, which is the classic peroxide. We've got an O2 paired with a double of an element from the first column on the periodic table. That is a big hint. This is going to probably be a redox reaction. So oxygen's -1, hydrogen's +1. Then the next thing is sulfuric acid. And working my way from the outside in, -8 contributed by the oxygen, +2 contributed by the 2 +1 hydrogens, so sulfur would have to be +6. Now we're going to take a look at the product. In the product, we've got manganese sulfate. Oxygen is -8. I don't know what manganese is going to be. This one's kind of a tougher one to figure out. So I'm going to, since between manganese and sulfur, sulfur's right below oxygen. Oh, I know how I'll figure it out. Sulfate, polyatomic ion, has a -2 charge. So if each oxygen has a -2 oxidation number, we've got -8. And the total charge of the whole ion has to be -2, so that means sulfur must be +6. And since the sulfate polyatomic ion's overall charge is -2, and we just have that paired with the manganese has to have an oxidation number of +2. So it looks like manganese did have a change in oxidation number. Manganese went from +7 to +2, so something to keep an eye on. Next compound, oxygen's an element. Hey, there's a change in oxidation number. We've got oxygen that's 0, and beforehand we had some -2 oxygens and some -1 oxygens. So oxygen looks like it went from -1 to 0. Moving along, I see a potassium sulfate. You know what? If you have a polyatomic ion, the oxidation numbers in that polyatomic ion are going to remain unchanged. So sulfur's going to be +6, oxygen's going to be -4, leaving potassium, the ion, to be +1. Water, oxygen's -2, hydrogen's +1. So we did notice changes in oxidation numbers. So to answer the question, is this a redox reaction? Yes, it is. Manganese, its oxidation number went from +7 to +2. That decrease in the oxidation number suggests that it gained electrons. And gaining electrons is reduction. And then oxygen went from -1 to 0, so it became more positive. It lost electrons, so it underwent the process of oxidation. So there's a few examples. Next, it'll be your turn to try.